Hello again. In this video, we're going to talk about concavity and inflection points. So let's talk about concavity first. So here's a definition of concavity. Let f be differentiable on an open interval I. If f prime of x is increasing on the interval I, then f is concave up on the interval I. If f prime of x is decreasing on I, then f of x is concave down on I. So let me show you a picture of the difference between concave up and concave down. So here's the sine function. In here it's concave up on this interval, and that's because the derivative is increasing in this interval. So you can see over here the derivative is negative, and it started to become less negative, and then eventually it's zero at the bottom, and then it starts to become more and more positive. And so I think you can see that the derivative is increasing in this interval. And the definition says that if f prime of x is increasing on an interval I, then f is said to be concave up on the interval I. Okay, so this function's concave up on this interval here. But then notice over here in this interval from 0 to pi, it's actually concave down. And that's because you can see the derivative is positive here, but it's becoming less positive, and then eventually it goes to 0, and then it starts to go negative, and it becomes more and more negative. And so that indicates that the derivative is decreasing, because it's going from a positive number to 0, and then it's becoming negative and more negative. So the derivative is decreasing in this interval. Again, if the derivative is decreasing on an interval I, then f is said to be concave down on I. Okay, so this part of the graph, it's concave down. Okay, now the definition of an inflection point. If f is continuous at C and f changes concavity at C, then f has an inflection point at C. So essentially, an inflection point is a point at which the graph of a function changes concavity. Okay, and then we have a test for concavity. Well, just to mention that a little bit more, if we go back to this graph up here, sine of x, you do have an inflection point right at the origin, because it's concave up in here, and then it's concave down in here, and it actually changes concavity right at 0 at the origin. And so that's an inflection point right there at x equals 0. Okay, now we do have tests for concavity, or a test for concavity. That's what theorem 410 is about. And so here's what that test says. Suppose the second derivative exists on an open interval I, and that the second derivative is positive on the interval I, then f is concave up on I. And if the second derivative is negative on I, then f is concave down on the interval I. Of course, if C is a point in the interval I at which the second derivative changes sign at C, then f has an inflection point at C. Now, let's see why this is the case, why this is a good test for concavity. So if the second derivative is positive on some interval I, the second derivative tells us the rate of change in the first derivative. Okay, so if the second derivative is positive, then it means the first derivative is increasing, is an increasing function. And like we said, if the first derivative is increasing on the interval, then by definition, it's said to be concave up on the interval. Okay, if the second derivative is negative on the interval I, then that indicates that the first derivative is a decreasing function on the interval I. And again, if the derivative is decreasing on the interval I, then by definition, it's said to be concave down on I. So that's why this test for concavity works. Okay, so I'm going to go through an example to show you how we actually find, we're going to try to find the intervals on which a function is concave up and concave down. And I'm going to show you an example of how we do that. But before we do that, I want to mention one more thing. There's several cases that you should think about when you think about inflection points. So here's an inflection point. And the reason it's an inflection point is because it's concave down over here, and then it's concave up over here, and so it changes concavity at this point. And it just so happens that the second derivative at this point happens to be 0. But the one thing you want to be careful about is just because the second derivative is 0 doesn't mean it's an inflection point. So here's an example over here where the second derivative at this point happens to be 0. Notice that it doesn't change concavity. It's concave up on this side and it's concave up on this side. So just because the second derivative is 0 at a particular point doesn't mean that that point is actually an inflection point. Another possibility is that the inflection point can occur at a place where the second derivative does not exist. And you can see that in this example, it's concave up here, and then it's concave down here. At this point in the middle where it changes concavity, the second derivative doesn't exist. But again, just because the second derivative doesn't exist doesn't mean that there's an inflection point at that spot. So for example, here you can see it's concave down over here, but it's also concave down over here. And the second derivative at this point in between does not exist. Okay, so just because the second derivative does not exist at a point, it doesn't mean there has to be a change in concavity. Okay, so the way we're going to work this out, the way we're going to run our test to determine where a function is concave up or concave down, is we're first going to find all the places where the second derivative is either 0 or doesn't exist, because those are candidates for places where we have a transition from concave down to concave up or vice versa. In other words, a possible inflection point or a candidate for an inflection point. But they're only candidates because it is possible that they don't turn out to be inflection points. Just because the second derivative is 0 or doesn't exist at a point does not mean it's an inflection point. Okay. If you do have a place where the function changes concavity, then that must occur at a point where the second derivative is either 0 or does not exist. That's why we're going to take the second derivative of the function and set it equal to 0, and then find out when the second derivative doesn't exist. And those are going to become candidates for inflection points, which I call possible inflection points. Okay, so let me show you an example where we work this out. Okay, so we're going to determine the intervals where this function is concave up and concave down, and then we're going to identify any inflection points that it has. Okay, so here's how we're going to do it. We're first going to take the second derivative of the function. All right, so the first derivative would be 20x cubed minus 60x squared. And then the second derivative would be 60x squared minus 120x. Okay, now we're going to find the possible inflection points, all the possible candidates for inflection points. Okay, so the candidates are places where the second derivative is 0, but also places where the second derivative does not exist. In this case, the second derivative always exists, so this never happens. Okay, so we don't get any possible inflection points in this particular case. But it could be equal to 0. So let's set the second derivative to 0. And then solve for the x values where that occurs. Okay, so we can factor out a 60x, and that leaves us with x minus 2. And then if you solve this, just divide this by 60, and you get x is 0. And over here, x minus 2 equals 0 just means x is equal to 2. Okay, so these are our possible inflection points. Remember, just because you found a place where the second derivative is 0 or doesn't exist, doesn't mean that it is an inflection point. The only thing we can say is that if we have an inflection point, inflection points occur at places where the second derivative is either 0 or does not exist. So these are the only possible candidates for inflection points. Now here's how we're going to determine whether they actually are inflection points. We're going to actually create a sign chart for the second derivative. And so what we're going to do is we're going to break up the number line into intervals based upon these possible inflection points. Okay, so the first interval is going to be from minus infinity to 0, and then 0 to 2, and then 2 to infinity. And then what we're going to do is we're going to pick test points in each of the intervals and plug them into the second derivative and determine whether the second derivative is positive or negative. If it's positive, by our test for concavity, if the second derivative is positive, that means that it's concave up. And if the second derivative is negative at a particular point, that means it's concave down. Okay, so let's try this. So a good test point in here might be negative 1. Okay, so I'm going to plug that into the second derivative. Okay, when you plug that into the second derivative here, you get 60 plus 120. Which is 180. And since the second derivative is positive, that indicates that the function is concave up. By theorem 410, the test for concavity. Okay, so let's pick a test point in here, like 1. Plug that into the second derivative, and you get 60 minus 120. Which is negative 60, and that indicates that it's concave down. In this interval. And then let's pick 3. That 3 is a test point in here. Plug that into the second derivative. And let's see what you get. 60 times 3 squared minus 120 times 3. Okay, so that's 9. Times 60 is 540, minus 360, and that gives you 180. And so it's concave up in here. Okay, so now let's see if we can't identify the inflection points. So at 0, it is changing concavity, right? It's changing from concave up to concave down. That's the definition of an inflection point, right? A point at which the graph changes concavity. It's called an inflection point. So yes, this is an inflection point, but this is also an inflection point at 2 because it does change concavity at 2 as well. So now we can declare that both of these are actually inflection points. Okay, but you don't know that until you actually do the sign chart. You actually have to see that it changes concavity. before you can declare it to be an inflection point. I mean, it's possible that you might get concave up, concave up, concave up. And if that happened, then 0 is not an inflection point and 2 is not an inflection point because it's not changing concavity there. There were possible inflection points, and further investigation under the sign chart shows that they would not have been inflection points. But that's not what happened. Under further investigation, the sign chart reveals that these actually are inflection points because it changes concavity at both of those points. Now, just to sort of reinforce this idea, here's the graph of the function that we were working with. So the graph looks like this. Now you can see that it is concave up in this region. And if you go back from negative infinity to 0, it's concave up. Okay, so this is concave up in here. But then from 0 to 3, in this interval, right, 0 to 3 in here, you can see that it's concave down. I'm sorry, 0 to 2, it's concave down. So it's changing concavity right here. You can see it's concave down here, and then it becomes concave up at some point, right? It's changing concavity right at 2. So it's now concave up in this region, in here. It's concave down in this region. Okay, so it's changing concavity right at x equals 2, right? It's going from down to up. Okay, so between 0 and 2, it's concave down, and then from 2 to infinity, it's concave up. That matches what we found in our chart. Now, one last thing. Eventually, we're going to start plotting these inflection points. Since these inflection points are important, we're going to want to plot them on a graph. So later on, you're going to want to know what the y values are for these. Okay, so in order to find the corresponding y values, of course, you would have to plug them into the original function. So when you plug 0 into here, you get 10. Okay, so as an ordered pair, the inflection point is at 0, 10. And then at x equals 2, there's another inflection point. But again, to find the y value, you would have to plug it into this function. And you can actually do that on a calculator. You have a TI-84 calculator, so let me show you how to do that. So the first thing you would do is go to y equals, and then type in the function, which I've done here already. And then you can go to the calculate button, which is the second button. So you got to press the second button first. Second, calculate. Then you get this menu here, and then just select value. And then it's going to prompt you for the x value, and we want to know what the y value is when x is equal to 2. And so I'm just going to enter 2 in, and the corresponding y value would be negative 70. Okay. So going back to here, if you plug a 2 in to this function here, you should get negative 70. Okay, so let me show you one more example. So let's say you have f of x is equal x to the 4th, and you want to find out where it's concave up and concave down. And then let's also find any inflection points that it has. Okay, so again, the way we're going to do this is we're going to first find the second derivative. Okay, so the first derivative is 4x cubed. The second derivative is 12x squared. And then we look at the two cases, right, when the second derivative is 0 and when it doesn't exist. Of course, this never happens because the second derivative exists for all x values. So you don't get any possible inflection points from this particular case. But notice that you do get one in this case, because if you set that to 0 and solve for x, you end up getting 0. Just divide by 12 and then take the square root of both sides. Okay, so this is a possible inflection point. But again, we don't know if it is or not until we do the sign chart for the second derivative. Okay, and so we're going to break it up into two intervals from negative infinity to 0 and then 0 to infinity. And we're going to test each of those intervals to see whether it's concave up or down. Okay, so we do that again by picking a test point in each of the intervals. So I'm going to use -1 for this one. And notice when you plug -1 into the second derivative here, you get a positive number, so it's concave up. Okay, and then I'm going to use 1 for this interval. And again, I'm plugging it into the second derivative here, and notice I get 12 again, right? So it's concave up in this interval also. Okay, so in this case, we don't have an inflection point at 0 because it's not changing concavity. In fact, if you graph x to the fourth, x to the fourth looks something like this. And you can see it's concave up throughout from negative infinity to infinity. And so it's not changing concavity at this point down here. So this just happens to be a place where the second derivative is 0. But it's not a point where we have an inflection point. So this is a good counterexample to keep in mind. Just because the second derivative is 0 or doesn't exist doesn't mean that you have an inflection point there. But if you have an inflection point, then the second derivative must be 0 or it doesn't exist at that point. And that's why this is simply a candidate. After you look at both of these cases, you get a list of candidates, right? Possible inflection points, which need to be classified as either being inflection points or not by looking at the sign chart. Okay, again, if you want to go back to these examples, that'll help reinforce the possibilities here. Again, it is possible for the second derivative to be 0 and for it to be an inflection point, like it is here. Or it could be the case where the second derivative doesn't exist and it's an inflection point, like it is here. But it's also possible for the second derivative to be 0 and not have an inflection point there. And that's an example of one right there. Or it could be the second derivative doesn't exist, like it doesn't here, because that comes to a sharp point. But it's not an inflection point because it's concave down on both sides. Okay, so I hope you found this video helpful. Thank you for watching. Bye-bye.